Okay, so these slightly harder ones. The first one, we're going to use some Pythagorean identities to help us out. So does everyone have your orange sheet out? If not, grab your orange sheet real fast. You're going to want it. We're going to use Pythagorean identities. Does anybody remember how many Pythagorean identities there are? There are only 3. You can manipulate them though, right? You can add or subtract to kind of change them, but at the core, there's only 3. The most commonly used one is sine squared plus cosine squared is equal to 1, and then there's one with tangent and secant, and then there's one with cotangent and cosecant that go together as well. So taking a look at this first question here, we have a sine squared trig function in there, and we have a cosine function. And right now, there's nothing that relates sine and cosine together except for a Pythagorean identity. But the relationship is sine squared and cosine squared, right? So what that means is we're not going to mess with this guy. There's nothing we can do with him. He's just going to chill there. But what we can do is we can mess with the sine squared. So what we're going to do is we're going to use the Pythagorean identity to take the sine squared and turn it into a cosine squared. And then our equation has all cosines in it. Does that make sense? What we're doing here? So the identity is sine. I'm going to change colors. Hold on. Sine squared of x plus cosine squared of x is equal to 1. That's the identity. Now, I have a sine squared in the equation, and I want to get rid of it. So what I'm going to do is I'm going to substitute with what sine squared is equal to. Well, right now it's sine squared plus cosine squared. So I can take that cosine squared and move it over to the other side, right? So I can say that sine squared of x is equal to 1 minus the cosine squared of x. And so what that means is I can take the sine squared of x in the equation, and I can take it out, and in its place put in 1 minus cosine squared. I'm going to substitute those. So we have the 2 in the front, and then we're going to take out the sine squared, and we're going to place it with 1 minus cosine squared. And everything else we will leave exactly the same. So what we have done is we have rewritten this equation by using a Pythagorean identity. And we have changed the sine squared into something involving cosine squared. So now my equation only has cosines. All right, if you have a cosine squared and you have a regular cosine, what are you most likely going to have to do to solve this? You're going to have to factor it, right? Whether it's a GCF or you have to use the big X, one of the two, you're going to have to factor it. So we're going to want to get this all looking nice and pretty so we can factor. So the first thing, let's go ahead and distribute. So multiply the 2, we'll have 2 minus 2 cosine squared x. And then the rest of the stuff. And then you can combine some like terms, right? The 2 and minus 3 is everybody say that 2 and minus 3? 2 in the very front, minus 3 at the end. We can put those together to make minus 1. So I'm just going to erase, if that's all right with you all, change it to a minus 1. And this is looking a lot better to factor, right? The only other thing you could technically do here is you see how it's a negative 2 in the front? You can factor with the negative 2 in the front, or you can say, I don't want to mess with the negative 2. And you could do something to change all the signs there, right? So do you want to leave the negative 2 and just go for it and see what happens so that you don't have to change it? Or do you want to do the extra step and change it? Extra step and change it? All right, so the extra step to change it is you literally divide everything by a negative 1. All the signs change. So essentially you're just taking this entire side, moving it over here. So instead of the 0 being on the right-hand side, the 0 is on the left-hand side, and all the signs change. So it turns into a plus 2, a minus 3, and a plus 1. As long as you change every single sign in your equation, you are good. And now we don't have to worry about the pesky negative. All right, we are ready to factor. This is a GCF or use the big X. The big X. You're going to take the 2 in the front and multiply it by the 1, so they multiply to be 2. Two numbers add up to be -3. What are they? -2 and -1. Do we all agree with that? Yes. So our factors are cosine of x minus 2, cosine of x minus 1. And you have to go back and take both of those numbers because we multiply by 2 at the beginning and divide them both by 2. All right, so the first one says cosine of x minus 1, right? That simplifies to a 1. So we're looking for where the cosine of x is equal to a positive 1, right? Because it said cosine of x minus 1 equals 0, add 1. So where is the cosine of x equal to positive 1? Where does that happen at? 0. At 0. Anywhere else or just 0? Just 0. Okay. So that's x equals 0 here. And then the next one is cosine of x minus 1/2 equals 0. So where does it equal a positive 1/2? Where does that happen at? Pi over 3 and 5 pi over 3. So pi over 3 and 5 pi over 3. All right, so they said, Miss Bird, that wasn't that much harder. It is a little bit harder because you had to use that Pythagorean identity at the beginning, right? But from there, after you got the Pythagorean identity in there, this could have been a question from yesterday, right? All right, I'll do another one with you. I'm going to do the one with the secant squared. Does that sound good? And I'll let you try the other one on your own. So what is the identity that relates secant and tangent, right? There's a secant squared and a tangent squared. What is the identity? Secant squared of x equals the tangent squared of x plus 1. So do we want to turn this equation into all secants or all tangents? We want to go all tangents, right? Because this tangent right here, that's just a regular tangent by itself, you're going to have a hard time changing that one because these are squareds. So we're going to change the secant squared into a tangent squared. So we already know secant squared of x is equal to this, so we're just going to substitute that in for the secant of x. So we'll say tangent of x, or tangent squared x, plus 1, and then you have that 1/2 tangent of x equals 1. All right, where to go from here? That's the Pythagorean identity, rewriting it, and then this could have been a question from yesterday. Subtract the 1. And what's really nice is this one and this one will both subtract and you'll end up with zeros, won't you? So we'll have tangent squared of x plus 1/2 tangent of x now equal to 0. And factor with a greatest common factor. Most likely, if you use the Pythagorean identity in there, you're replacing squares, so most likely you're probably going to have to factor. That'll probably be where you're going. And there's only 2 terms, so we don't have to use the x. That's when you have 3 terms, right? So just greatest common factor. They both have a tangent. So if you have a tangent squared and you take out a tangent, you're left with just tangent, and then 1/2 tangent. If you take out the tangent, you're left with a 1/2 equal to 0. So then the first piece is, where is the tangent of x equal to 0 at? Where does that happen? At x equals 0? because that's where the sine is 0. So for tangent to be 0, sine has to be 0. So at 0, anywhere else? And at pi, sine is also 0 at pi. So 0 and pi. And then the other side of this, tangent of x plus 1/2 has to be 0. So we can say the tangent of x needs to be a negative 1/2. And where does that happen at? Tangent of x negative 1/2. It's not on the unit circle, is it? Now the question is it possible for the tangent of x to be negative 1/2? Is it possible? Because was it yesterday I think we came across one where it said like cosine needed to be negative 2 and that just wasn't possible, right? So is it possible for the tangent to be a negative 1/2? What does the graph of a tangent function look like? Yeah, it's the ones that run up and down, right? And if it goes up forever and down forever, is there any numbers that it can't be? No, it can literally be anything. The only thing here is that this is just not a nice number, is it? It's not like a pi over 3 or a pi over 4 or a pi over 6. So how can we figure out what angle that actually happens at? We've solved this before. How can you solve for an angle?
You need to take it's the one where it's like the negative 1 of tangent.
Yes. What's the negative 1 of the tangent called when you have tangent to the negative 1? The inverse. So you're going to inverse this. So you can tangent inverse. I already have it here. Tangent inverse. Remember that was, you hit the blue button and then the tangent button. Tangent inverse of negative 1/2 is negative 0.43, 0.464 if you round it. And so this is an angle. It's in the negatives, which means it goes back this way, right? But technically that angle has a tangent of negative 1/2. Yeah. I know it's not between 0 and 2 pi, but we're going to throw it down anyways. Negative 0.434, or was it 64? 64, wasn't it?
Yeah.
I think I'm just way off. Hold on. 464. And that is in radians. I made sure my mode was in radians. I'm a calculator. And so technically they gave you an angle down here. You could find the positive version of it by doing what? Find the coterminal, right? This angle down here has a coterminal angle in the positives, which would mean to add. Don't add 360. We're not in degrees. Add 2 pi. We're in radians. So if you take this value right here and you add 2 pi, there is a positive angle between 0 and 2 pi that has a tangent of a negative 1/2. So we could say, instead of this one, 186, if I remember correctly. 18. Ooh, I wasn't close. 0.82. I have an extra one. There we go. 0.82. All right. You will see a couple of these pop up every once in a while. And you can just use your calculator to inverse those, right? It doesn't happen very often, but hey, every once in a while, sometimes you might get a value that's not on the unit circle. It doesn't mean there's no solution there. There could be no solution, but all right. You try that one over there. Cosine squared x equals 1 minus sine of x. Give it a shot. See what you come up with. to replace the cosine squared with 1 minus sine squared? Because the other side had just a sine on there, that's how we knew that the cosine squared needed to be replaced with a sine squared, so that we would have all sines. All right, so my first line is what I got after the replacement, and then I realized, hey, 1 and 1, right? Those make 0, and so now I'm looking at just a sine squared and a sine, and so I'm thinking in my head I have to factor this. So I went ahead and said these two make 0 together, and then this one I don't want it to be negative. I want to move it over and make positive, so I have a positive sine squared of x, and then this minus sine of x. And then from there, it turns into a problem from yesterday, right? They had a greatest common factor, so take out a sine of x. Left is a sine of x minus 1. So where is sine of x equal to 0, and where is sine of x equal to 1? So what were the solutions you got for this? 0, pi, and pi over 2, and that's it, right? 0, pi, and pi over 2. How did it go? Was it all right? Did we do okay with it? Cool. All right, so we're going to move on to this next idea. So here we have a cosine of x plus 1 and a sine of x. And this is slightly different than the last problems, because the last problems we had some kind of square, didn't we? So the problem here is we don't have a square. Is there anything that relates sine and cosine together?
Sine theta equals theta? No.
Yeah, so sine of theta equals cosine of theta minus 90. Is that minus 90 or minus pi over 2, right?
90 minus theta.
Oh, 90 minus theta. So those are cofunction, right? So the only relationship we have between sine and cosine is cofunction. Now, do you think this is going to get easier if we start putting in like 90 minus thetas or pi over 2 minus thetas inside of our trig functions? No, because we're not going to have like terms, because one will have an x, the other one will have like an x and a pi over 2 or an x and a 90. And so that's not going to make it any easier. So cofunction identities aren't really going to help us here, which really means that the only relationship we know between sine and cosine is the Pythagorean identity, right? So go back to your Pythagorean identity. Sine squared plus cosine squared equals 1. Now we can edit this equation and get some squares in there, right? You are mathematically legally allowed to square both sides. That's always an option. And if you square both sides, you're going to end up with some cosine squareds and some sine squareds. And so this strategy is to make this look a lot messier by squaring both sides. Yeah, so if you have a relationship here where it's not looking good and there's nothing that relates those two things together, you can always square both sides if there's a Pythagorean identity that could possibly relate them. When you square these, you have to be extra careful, right? Cosine of x plus 1, that quantity squared. You have to think about it as the cosine of x plus 1 times the cosine of x plus 1, which means you have to distribute, yes? You're going to have to do all the multiplication here. Okay, if you just square the cosine and just square the 1, you're going to miss the entire term in the middle. All right, so cosine of x times cosine of x is a cosine squared of x. So that's the first one. And then you have cosine of x times 1, and 1 times a cosine. So you have a cosine and another cosine, and they're being added together. So you'll have plus 2 cosines of x. And then you'll have a 1 times a 1, which is a plus 1. So when you square something with a plus sign in the middle, you should always end up with 3 terms and not 2, right? If you end up with 2, something alarming is happening, and you are missing something. All right, the good news is when you square the other side, that's just the sine of x. So when you square that, you just have sine squared. So yes, it looks a lot messier than when we started, right? All right, so next question is, where should we go from here? Turn the sine squared into cosines, right? We have a cosine squared, which we could change to a sine, but then we have just this cosine, which means we want everything to be cosines. So change this guy into a cosine. So what does sine squared change into? 1 minus cosine squared of x. So we're just going to substitute to get rid of that sine squared and change it to a 1 minus cosine squared. All right, where do we go from there? Set it equal to 0 because we're probably going to have to factor this, right? We have a cosine squared, we have a cosine. Anytime you have two cosines or sines, two trig functions, but one's squared and one's not, you're going to want to factor most likely. So if I add a cosine squared over, I'm going to have two cosine squareds on this side. And I have two cosines. And then this is really nice. The 1 and the 1 will simplify to make zeros, won't they? Anytime you can get terms to simplify like that, it's a good day. All right, we're getting really close. There's a greatest common factor. You only have two terms here. They both have cosines in them, so you can take that out. Also, I would take out the 2. Yeah, they both have 2's. So 2 cosine of x is coming out. So you're left with a cosine of x in the first one and just a 1 in the second spot. So you're looking for where 2 cosine of x is equal to 0. By the way, 2 cosine of x equal to 0 is the same as where is cosine of x equal to 0, right? So the 2 is not really doing anything as that greatest common factor. So the answers from this first one, where is the cosine of x equal to 0? That is at pi over 2 and 3 pi over 2. Pi over 2, 3 pi over 2. And then the other side, the other factor, cosine of x plus 1, where does that equal 0? So that's where the cosine of x is equal to negative 1. And cosine of x equals negative 1 at pi. And that's it, nowhere else, right? Just pi. So 3 solutions from that question. So a little bit harder because you have all this extra multiplication, right? So technically we had the multiplication here, we had a Pythagorean identity in here, and then we also had the factoring. So that's why I call this challenging, because it's a little bit harder than everything we've done before it. Question?
I like to think that math never gets harder, it just gets longer.
It just gets longer? True. It just adds more steps, right? Right. Technically, all of the algebra we've done, though, you've done just not with trig functions, right? You factored, we've distributed before, we've done all this stuff. We just haven't done it with trig functions. So, all right, I'm going to let you try this one down here, but I'm going to give you one piece of advice before you start. You do not want to square two trig functions together. It's not going to turn out nicely. So you want to move one of them over. It does not matter which one you move over. So I'm going to move the cotangent over. And when I do that, it turns into 1 minus the cotangent of x. You are much, much, much better off splitting your trig functions up than trying to square them on the same side. It is possible to do it on the same side. I'm not saying it's not. I'm just saying you're going to make your life a lot harder if you try. All right, I'll give you a few moments. Go ahead and give that one a shot. See what you come up with. If you want to check your work after the squared part, I do have that up on the board now. So don't look if you're not done squaring both sides. But if you've squared both sides and you want to check and make sure you got it, it is up yonder. Did you all turn everything into cosecants or cotangents? Cotangent. So you replace this one over here. So the cosecant squared is equal to the cotangent of x plus 1, right? Or 1 plus, it doesn't matter because it's addition. And so that was, this whole side stayed the same. All right, and then it's looking like some really nice things are going to happen, aren't they? The cotangent squared on this side will simplify with the cotangent squared on this side, won't it? And they'll make 0. So cotangent squareds are out. This one and this one are going to simplify as well and make 0. So I have 0 left over here. And the only thing left on this side is the negative 2 cotangent of x. So it got really messy, but there was a bunch of things that simplified, wasn't there? All right, in this case, you can divide by 2, negative 2. So we want to know where is the cotangent of x equal to 0. So where does that happen at? Cotangent of x equal to 0. Pi over 2 and 3 pi over 2, because cotangent is cosine over sine. So where's the cosine equal to 0? Pi over 2, 3 pi over 2. All right, any questions y'all had on that one? Came up. A lot of algebra before you get to a pretty basic solving here, right? Yes. But if you can't get through that, then it's kind of tough. All right, and last but not least, this guy right here, sine and cosecant. So, do we want to square both sides? What are y'all thinking? Same thing as all the other ones, square both sides, keep going? Is there a Pythagorean identity that relates sine and cosecant? No. So will squaring both sides help us? No, it's just going to make things messier. In both of these problems, there was an identity, a Pythagorean identity that related sine and cosine, and there was a Pythagorean identity for cosecant and cotangent together. Now, on this one, there is not a Pythagorean identity that is sine and cosecant. Yes?
You just turn that into a 1 over sine?
Cosecant is the reciprocal of sine, isn't it? So there might be some distractors in here where, hey, you might think that you should square both sides and maybe use a Pythagorean identity or something. But if there's no identity that relates them, a Pythagorean identity that relates them, look at some of your other identities. And this is a reciprocal, isn't it? So you can change this cosecant right here to 1 over the sine of x. So we still have an equation that only has signs in it. And we did not have to move anything over or square both sides or anything crazy like that, because cosecant and sine, their relationship was identity, or the reciprocal identity relationship there. All right. Now the question is how do we solve this? Multiply everything by the sine of x. Why? Because sine of x is in the denominator. And how do you get rid of denominators? You can multiply everything, right? So sine of x times 2 sine of x is 2 sine squared of x. Sine of x times 1 over sine of x is just 1. And sine of x times 0 is just 0. So we cleared our denominators. And then this is actually something that you saw before, right? Subtract 1, divide by 2. So sine squared of x equals a negative 1/2. And then take the square root. Whenever you take a square root, you include plus or minus. What's the square root of a negative 1/2? Ooh, it is imaginary. Can you square root a negative number? No. So it's really easy to get that negative and just think about that negative goes in with these and then you're good, right? If that was a positive 1/2, it'd be square root of 2 over 2. But it's not. It's a negative. And so I tricked you, stumped you a little bit. And yeah, you can't square root a negative number, right? And so the problem with this is this would be an imaginary square root of 2 over 2. And we're not going to worry about solving where sine functions are imaginary at. So we're going to go ahead and say that there is no solution here. So there is no value that this equation will be true for. It's only true for imaginary numbers. And we don't need to get into imaginaries in the world of trig functions, right? Let's not go there. Toby's like, no. let's not mess with it. All right. So that's all I have for you in terms of notes. So your assignment is just the next page. It's page 29. There are 8 of them, and that's it.